Common source stage. The common source topology exhibits a relatively high input impedance while providing voltage gain and requiring a minimal voltage headroom. As such, it finds wide application in analog circuits and its frequency response is of interest. Shown in figure is a common source stage driven by a finite source resistance Rs. We identify all of the capacitances in the circuit, nothing that CGS and CDP are grounded capacitances, while CGD appears between the input and the output, assuming that lambda is equal to 0 and M1 operates in saturation. Let us first estimate the transfer function by associating one pole with each node. The total capacitance seen from X to ground is equal to CGS plus the Miller multiplication of CGD, CGS plus 1 minus AV CGD, where AV equal to minus GMGD. The magnitude of the input pole is therefore given by omega n is equal to 1 by Rs CGS plus 1 plus GMGD CGD. As the output node, the total capacitance seen to ground is equal to CDB plus the magnitude plus the Miller effect of CGD CDP plus 1 minus AV power minus 1 CGD similar to CDP plus CGD. Thus omega out 1 minus 1 by RDCDB plus CGD. Another approximation of the output pole can be obtained if Rs is relatively large, simplifying the circuit as shown in figure. Where the effect of Rs is neglected, the reader can prove that Zx equal to 1 by C equivalent S ratio CGD plus CGS by CGD into 1 by GM1, where C equal to CGD CGS by CGD plus CGS. Thus the output node is roughly equal to omega out is equal to 1 by RD, similar to CGD plus CGS by CGD into 1 by GM1 C equal plus CDB. Here you can see in this figure high frequency model of a common source stage. Model for calculation of output impedance. Figure equivalent circuit of figure. We then summarize that the transfer function is V out by V in into S is equal to minus GM RD by 1 plus S by omega in into 1 plus S by omega out. Note that RO1 and the load capacitance can easily be included here. The primary error in this estimation is that we have not considered the existence of zeros in the circuit. Another concern stems from approximating the gain of the amplifier by minus GMRD, whereas in reality the gain varies with frequency. For example, due to the capacitance at the output node. Now we obtain the exact transfer function. Investigating the validity of the above approach using equivalent circuit depicted in figure, we can sum the currents at each node Vx by Vx minus V by Rs plus Vx CGS plus Vx minus Vout CGDS equal to 0. Vout minus Vx CGDS plus GM Vx plus Gout 1 by Rd plus CdBs equal to 0. From equation, Vx is obtained as Vx equal to minus Vout CGDS plus 1 by Rd plus CdBs by Gm minus CGDS, upon which substitution in equation yields minus Vout Rs power minus 1 plus CGD plus CGS plus CGD as Rd power minus 1 plus CGD plus CdBs by Gm minus CGDS minus Vout CGDS is equal to V in by Rs, that is Phi out by V in S is equal to CGDS minus GMRD by Rs Rd gamma S square plus Rs plus Rs 1 plus GMRD CGD plus Rs G CGS plus Rd CGD plus CDB into S plus 1, where gamma is equal to CGS CGD plus CGS CDB plus CGD CDB. Note that the transfer function of is of second order even though the circuit contains 3 capacitors. This is because the capacitors form a loop allowing only two independent initial conditions, allowing only two independent initial conditions in the circuit, hence yielding a second order differential equation for the time response. If manipulated judicially, equation reveals several interesting points about the circuit, while the denominator appears rather complicated. If it yields intuitive expression for the two poles omega p1 and omega p2, if we assume omega p1 mod omega p1 less than mod omega p2, writing the denominator as d equal to s by omega p1 plus 1 s by omega p2 plus 1 is equal to s square omega p1 omega p2 plus 1 by omega p1 plus omega p2 s plus 1. We recognize that the coefficient of s is approximately equal to 1 by omega p1. If omega p2 is much further from the origin, it follows from equation that omega p1 is equal to 1 by rs1 plus gmrd cgd plus rs cgs plus rd cgd plus cdb. How does compare with the input pole given by equation? The only difference results from the term RDCGD plus CDP, which may be negligible in some cases. The key point here is that the Intuitive approach of associating a pole with the output node provides a rough estimate with much less effort. We also note that the Mailer application of CGD by the low frequency gain of the amplifier is relatively accurate in this case. From equation we can also estimate the second pole of the CS stage of the figure, since the coefficient of S square is equal to omega p1 omega p2 power minus 1. We have omega p2 equal to 1 by omega p1 1 by r srd cgs cgd plus cgs cdb plus cgd cdb is equal to rs1 plus gmgd cgd plus rs cgs plus rd cgd plus cdb by rsrd cgs cgd plus cgs cdb plus cgd cdb. If CGS is very much greater than 1 plus GM RD CGD plus RD CGD plus CDP by RS, then omega P2 is equal to RS CGS by RS RD CGS CGD plus CGS CDB is equal to 1 by RD CGD plus CDB. Same as equation we as the output pole approach is valid if only CGS dominates the response. The transfer function of equation has bits 0 given by omega z equal to 1 plus gm CGD, an effect not predicted by simple approach leading to equation located in the right half plane. The 0 arises direct coupling of the input of the output through CGD as illustrated in figure. CGD provides a feed-through path that concludes the output signal at the input signal to the output at very high frequency, resulting in slope the frequency response that is less negative than minus 40 dB by decimals. As explained in chapter 10, the A0 in the right half plane introduces stability issues in feedback amplifiers. As you can see in this figure, feed forward through CGD log scale. In this figure, calculation of the 0 in a CS stage. The 0 S that can also be computed. Nothing at the transfer function V out S V in S must drop to 0 for S equal to ZS for finite. Vn means that V out Zx equal to 0, and hence the output can be shorted to ground at this possibly complex frequency with no current flowing through the short. Therefore the currents through CGD and M1 are equal. And opposite, V1 CGD SZ equal to GM V1, and that is SZ equal to plus GM by CGD1. In high-speed applications, the input impedance of the common source stage is also important. As first-order approximation we have from figure A, Zn equal to 1 by C Gs plus 1 plus Gm Rd Cgd into S. But at high frequencies, the effect of the output node must be taken into account, ignoring CGS for some moment, and using the circuit of figure B, we write S minus GMVX RD by 1 plus RD CDB S plus 1 plus Ix by C GDS equal to Vs, and hence Vx by Ix equal to 1 plus Rd CGD plus CDBS CGDS 1 plus GMRD plus RDCDBS. The actual input impedance consisting of parallel combination of equation and 1 by CGSS. In this figure, calculation of input impedance of CS stage at the frequency where mod RT C GD plus C dBs very much less than 1, and mod RD C dBs very much less than 1 plus GMRD. Equation reduces to 1 plus GMRD C GDS power minus 1 as expressed, indicating that some impedance is primarily capacitive at higher frequency. However, equation contains both real and imaginary parts. In fact, if CGD is large, it provides low frequency path between the gate and drain of M1 yielding the equivalent circuit of figure C, suggesting that 1 by GM1 and RD appear in parallel with the input. Thank you.